This conference will now be recorded
and posted on YouTube afterwards. Everyone who speaks during today's event will be part of the recording. We will do the Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if your camera is on, will be part of the recording. If you do not ask a question, you will not be part of the recording. If you're using the most recent version of the app, which we do recommend, you can use the raise hand function to join the queue. If you're using an older version of the app which does not have this function, please use the chat to let the organizers know you would like to ask a question, and they will add you to the queue. The organizer will let you know when you are next in the queue, so you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we're monitoring during the presentation. SFPUG, Bay Area Postgres, is a PGUS affiliated user group, and I am a volunteer for PGUS. SFPUG is sponsored by PGX, and I work for PGX. And without further ado, here is Philippe Nöel with BM25 full text search in Postgres by Tantivy.
Hey everyone. Here we go.
Yeah, there you go.
I was just going to ask. Thank you so much.
You're welcome.
Let me find the right one. Here we go. Can everyone see this?
Yes.
Okay, perfect. Hey everyone, it's super nice to be here. So my name is Philippe. As Catherine said, I'm one of the makers of a Postgres project called ParadeDB. We build a Postgres extension to do fast search and analytics in Postgres. And today I'm going to be telling you a bit more about search in Postgres, if you're not as familiar with it. So we'll talk about the current state of full-text search in Postgres. We'll talk about what's missing and why it needs to be better. We'll talk about our work. So our company is called ParadeDB. We build an extension called PG Search, which we build to solve these limitations. In order to do that, we use a library called Tantivy, which was in the title, and I'll cover what that is. And finally, we'll cover a few of the use cases that people find today for the work that we do. If you want to stop me at any time, feel free. I'm on a single monitor setup, so I can't see the videos. I'm only seeing my own screens right now. So maybe just shout, or I don't know if Catherine will do the monitoring, but I can't see the raised hands. I apologize for that.
No worries, Philippe. I'll take care of that.
Okay, thank you. I appreciate it. But that's it. So without further ado, let's get into it. So before we get going, a couple of jargon. So full text search, for those that are not familiar, is the technology behind a lot of the search functionalities that you see in applications today. So when you go on Facebook, and you search for someone's name, or you go on Amazon and you search for a product, that's powered by full text search, amongst other things. And here's some jargon that people typically use and that we'll be referring to in the talk, so that we all know what we're talking about. First thing, tokenization. That's the concept of splitting words into searchable chunks. It can be subset of words, it can be full words. Stemming is reducing a word to their root form. So the stem of the word running, for example, would be run, R-U-N. An inverted index is a data structure that makes it very efficient to do full text search. Faceting and aggregation is the concept of doing filtering or bucketing of results. So if you think of like excuse me, an e-commerce catalog like Amazon, you might want to bucket by star rating of the products, right? 4-star and up, 3 stars and up, things like that. And then lastly, the Elastic DSL. So Elastic is a popular search engine that is used to build those experiences. And the DSL is their own domain-specific language. We'll be referring to kind of our own equivalent that we bundle into Postgres. So a bit more about me. My name is Philippe. I'm one of the founders of ParadeDB. I'm originally from Rivière-du-Loup, Quebec. Before that, I worked at Azure, and then I worked in the browser space. And if you want to know more about me for some reason, I did one of those Postgres live interviews that you can find online. And then ParadeDB, as I said, we're an Elasticsearch alternative on Postgres. We're packaged at a Postgres extension. We have two. Today we'll talk about PG Search, which is the core of what we do. And we're built in Rust because, who isn't nowadays? Couple of reasons why people use us. I found while giving these talks that sometimes people find it interesting before we dive into it, the sort of why behind it. So a lot of users move from Elasticsearch to ParadeDB. We try to be sort of a replacement alternative for them. One of the big benefits they get is the reliability of Postgres for transaction safety. Elastic is known for not being super reliable, and obviously, if you're here, you know that Postgres is amazing at this. So that's a big one. Data freshness is another big one. Oftentimes, when people use Elastic, they move data from Postgres to Elastic, either in real time or on like a schedule. You don't need to do this, of course, if you're using it directly in Postgres, but that saves a lot of headaches and it makes the data searchable faster. And then you also have the full benefits of the features of Postgres, right? You can do joins with your full text search data. Most search engines today are NoSQL databases. Some people don't believe NoSQL are databases, but they can't do joins. And that's a big sore point for all these folks. And then the last thing before we really get into it, I don't work on ParadeDB alone, and I'm not even the primary person building the core of ParadeDB at this point. So I also work with Ming, who's on the left, Neil, Eric, and myself. We're the main four people behind it. The slide is a bit out of date. We hired a new person called Itai, who should really be on here. So that's on me. I should have fixed this. And some of you may know Eric. He was previously the maker of a project in a similar vein called ZomboDB. And he's also the primary author of PGRX. PGRX is a framework for building Postgres extensions in Rust. It's what we use. A lot of companies in the Postgres world use them now. So he's a bit of a legend in the space. Okay, let's get into it. So what is full text search? I touched on this a bit before, so we'll go over that one pretty quickly. But basically, full text search is the technology for querying documents based on keywords or phrases. There's two core concepts of it. There's processing the data to make it easy to search later. And then obviously there's the searching step. It can be super simple, right? Like search in a document for the word cheese, or it can be super complex. You might want to search in different languages. You might have multiple languages within the same text. You might want to return the results in a different order depending on a variety of factors like the language, other traits associated to it. We worked with companies, for example, in the music industry where based on the number of plays on a specific song, they might want to return it higher, right? So you can do a very, very complex experience here. Obviously, it's 2025 now, and AI is everywhere. And so a lot of people have also heard of a concept called vector search. Vector search is a complement to full text search. It's also known as similarity search. It matches documents based on their semantic meaning. So like how close the meaning of a specific keyword or specific document is to the query. And it's often used alongside full text search to provide even better results. pgvector is the Postgres extension that does it. We don't do anything with vector search ourselves. Our customers and our users typically use this alongside pgvector. And this presentation is not on vector search, but it's a related concept. So, good to know about. Okay. First thing, the state of full text search in Postgres. So what can you do today in any single Postgres that you run anywhere? There's three main things. The first one is the like operator. That's sort of the most basic full text search you can do. We have tsvector with a gin index. That's sort of the standard full text search in Postgres today that people might think about. And then lastly, there's something called pgtrigram, which is an extension that was brought into core Postgres, which allows you to do some slightly more complicated full text search on top of the basic tsvector. How do they work? So the like operator has the following syntax. So column name, like pattern syntax. An example query might be something like select everything from users where the name is like John with an ampersand. And this will match keywords like John, Johnny, Johnson, things like that, right? So it has some basic ability to sort of expand the keyword. The benefit is it's very simple, right? The limitation is it can be quite slow if you have a lot of data. It's very, very limited in functionality. So as I was mentioning before, some people might want to rank based on a variety of things that come to with a keyword. And what the I like pattern, it doesn't have any way to do relevance scoring. You can't really tweak how the results are returned super well. But, it's a good way to get started. Most people who do search in pure Postgres today do it with TS-vector. So that's sort of the real implementation. So it stores the tokenized TEM representation of text. If you remember the jargon that I was just talking about at the beginning, it means that the words, the full sentences or the full text corpus is split into tokens, let's say tokens as defined in the English language, right? And then there are stems so that they're shortened to their core form so they can be matched more easily. The results are then returned based on an algorithm called TF-IDF, term frequency inverse document frequency. In short, what this means is the more often a keyword is in the corpus of data, the higher it should rank. Makes sense, right? So if you're searching for the word cheese and you have a row in your Postgres that has the word cheese mentioned many times in the text, it's probably more relevant to the user. And then to balance that, there's the other part, inverse document frequency, which means the less frequently a term is within the entire corpus, the higher it should rank. This is used to account for words like the, for example, right? That's probably a word that's going to be there very frequently in all the documents. So it doesn't convey a lot of information on how valuable this information is to the person doing the search. Right? But if you have a word like cheese, which is very present in a few documents, but not very present in the rest of the text corpus, probably it should be higher in the result set. So that's how it works at a high level. And then the GIN index, that's an index that's built into Postgres as well. You can use it to create this inverted index, this efficient data structure to search over the columns, which can greatly improve the performance at scale. When people sit are doing full text search in Postgres today, this is what they're doing. On top of this, as I was mentioning, there's a third way you can do full text search, which is something called pgtrigram. What this does is it tokenizes the words into groups of 3 characters. So if I take the example of cheese again, the trigrams for cheese would be CHE, the first 3 letters, HEE, the second group of 3 letters faced off by 1, EES, and then finally ESE. This can be useful to do things like auto-completion. So if you go on Amazon and you search for something, it's going to start to give you suggestions right away, right? That's, even before you're done typing. That's an example of a more complex feature of full text search that you can do, which is very important to customers. And pgtrigram gives you a basic ability to do this. So if I type something like CHEES, I didn't type cheese perfectly, but you can build an experience on top of it that enables your application to return results for cheese. Any questions so far? Okay. So now that we've covered the main 3 ways you can do full text search in Postgres, let's talk about what they're missing. So first of all, Postgres full text search is good. There's a lot that you can do with it. You can get quite far with it. There are people with hundreds of gigabytes in their Postgres databases that get a lot of mileage out of this functionality, but it's not perfect. So the first big sore point for Postgres full text search is something called BM25 relevance. Excuse me. So TS-vector uses an algorithm that I mentioned called TF-IDF. It turns out most search databases in the world use something called BM25. BM25 is a generalization of the TF-IDF algorithm that is used to account for 2 problems with the algorithm. For those of you that are curious, you can think of how I defined that algorithm before and think of ways in which you might think of potentially gaming the system to sort of make sure your results rank higher, even though they maybe shouldn't. And we'll cover that on the next slide. So the results would be better. The second thing it's missing is tokenizers and token filters. Today, there's a lot of different types of textual data. You can write code, you can write medical, you can write in tens or hundreds of languages, right? And being able to tokenize these differently is really important. Postgres full text search has some basic way to tokenize other non-English languages. It excels at English, but there's pretty big limitations. It also doesn't have the ability to do like a proper like search database complex query or advanced text queries. So as I was mentioning, based on your use case, you might want to say, hey, I want to modify the results or re-rank the results based on my use case. Because I am Spotify and I know that even though there's another song that has, a more close textual match to what the user is searching, probably I should show the song that has 2 billion listens at the top, because that's way more likely to be what the user is searching. For example, I'm making this up. Postgres doesn't have a really good way to do this. And then the last thing is it doesn't have a good way to do the bucketing. I mentioned the faceting with the aggregations. If any of you have tried to do a count star query in Postgres before, you know that over large amounts of data, hundreds of millions of rows, it gets really, really, really slow. And so that doesn't work too well, and that's very, very common in proper search databases. These are the 4 big things that it's missing, and they're the 4 things that we work on to try to improve and make Postgres capable of doing all of this and really stand as a search database compared to Elastic and all the other ones that exist. So BM25, what is it? You didn't think you would see Matt today, but here it is. You don't have to pay too much attention to it, though. There are 2 big problems with the TF-IDF algorithm, as I defined it before. The first big problem is something called term saturation. So if you remember what I was saying, the term frequency said the more frequently a keyword is in the document, the higher it should be on the list of results. That's fair enough, but let's say I have a document that has 1,000 mentions of the word cheese, and another one that has 1,005 mentions of the word cheese. Well, probably at that point, the extra 5 don't really give you a lot of detail or a lot of information on whether this is a better or worse document. So BM25 accounts for term saturation. It's basically saying at some point, if you have a lot of words, a lot of repetitions of the words, it shouldn't impact the score too much. So you can see on the bottom part here, it's kind of tapering off as you go, right? It's not a linear relationship. The second thing that it's accounting for is the document length. Obviously, if you're searching through documents and one is 100 words and the other one is 100,000 words, you're way more likely to see the results very often in the longer document, right? But just because it's longer, it doesn't really mean it's what the user is searching for. And so BM25 accounts for this by taking sort of the average length of documents to have sort of an even point of comparison. And this can drastically improve the search results and make sure that you get something that's more like what the user is searching for, rather than just getting, 100,000 pages of documents with the word cheese a million times in it, because that wouldn't be a really good experience. This is the state of the art for search today. It's still quite simple, frankly, but it's the state of the art for search today. Most databases that implement full text search do it this way. And this is what we do at PG Search. So as I mentioned, ParadeDB, we're a startup, we're building PG Search. We bring this BM25 algorithm to Postgres, and in order to do that, we use a library called Tantivy. So Tantivy is a search library that's written in Rust. We build our Postgres extension in Rust, and we do a lot of work to sort of integrate it deeply within Postgres. If any of you have worked with Postgres internals before, you know that this is far from easy. It's a decent amount of work. So Tantivy, what it does is it's heavily inspired by a library called Lucene. Lucene is the library that Elasticsearch uses, the most popular search database. It supports BM25 algorithm. It supports fast full text search. It supports the faceting, the bucketing, the aggregations that I mentioned. It has the inverted index that I mentioned. It has basically everything, frankly. But it's not compatible with Postgres, so that's the work that we do. And Postgres, on the contrary, doesn't have these features built in. The way we sort of glue the two together is with 4 core Postgres internals APIs, which is what I'll talk about in the second half of this talk. The first is our own operator called the @ operator. We've inspired it off of tsvector. For if any of you have done full text search in Postgres, you know the operator for tsvector is the double @ So we figured we would, stay with the conventions and add an extra @ sign. The second thing we do is we bring a custom index. So as we were mentioning before, an inverted index is really important for the performance to be good. It's a data structure that stores the mapping of the keywords to where in the corpus that it is. And we sort of integrate the Tantivy inverted index as a Postgres index or a custom Postgres index using the index access method. The third thing we do is we integrate a pretty thorough query builder API. So that's to solve the issue of Postgres not having the ability to do these really complex query logic that a Spotify or an Amazon or a Best Buy might want to do. And then lastly, we have a custom scan, which dictates how we scan data in the tables to then process it and return it to the user in an easy way, the database user in this case. Any questions before I go into the sort of how we built it? Okay. So the first thing we do, we introduce a custom full text search operator. So our @ operator, what it does basically is it compares the query that a user might ask, let's say the word cheese, and it compares it against the corpus of data that we have, and it tells you that it's true if it found it, right? You can add it to any Postgres query. Any single Postgres query that you run today, if you add the PG search extension, you can now also augment it to be able to do this matching. Just the same way you would add a where clause or any sort of standard Postgres SQL syntax. Here's an example query. You might say, select star from mock items where the ID is smaller than 10 and the description @ keyboard. So in this case, we're searching for the word keyboard in the description of some product list, right? Let's say the Best Buy catalog. You can add it with joins, you can add it with order bys, group bys, anything. One of the really powerful features of this is the ability to do joins, right? And not need to denormalize your tables. On top of this, so that's the basic set to just be able to do search queries. Behind the scenes, it's powered by Tantivy. On top of this, we want to make sure that it's fast, right? So if we were just using the @ operator with nothing else, every time a user would run a query against the database, it would need to look through every single row in the table, right? In this case, in the mock items table. Obviously, that's slow, and it's called a sequential scan in Postgres. So just looking row by row through everything. We can do a bit better. So what we can do is we create what we call a BM25 index, which creates this inverted index I mentioned over the over the table. It's just like any other Postgres index. So like a B-tree index, if you've used those, a GIN index, a GIST index, so on. You can do updates, you can do vacuums, you can do scans. It's just Postgres at the end of the day. The one exception is we recommend creating a single index on your entire table. So that's why we call it a covering index. You should put all the columns that you want to search over from your table directly within the index. The reason behind this is the BM25 algorithm, the way it works is it maintains statistics on term frequency across the entire corpus. And if you have everything within the same index, it can do that more accurately and give you better results. So we add this on top of our @= operator, and then instead of needing to do a sequential scan, we just need to do an index scan, right? So it queries the index, and the index has some way to map, okay, different keywords are in different parts of the corpus. I don't need to scan the entire table. I can only scan part of it. That gives significantly faster performance. And if you've used any of the initial full text search in Postgres that I mentioned earlier, like tsvector, you know that if you use it without the GIN index, it's significantly slower. Same deal here, but for BM25 index. Third component that we add is what we call the Query Builder API. So users might have really complex ways to do queries, and we want to make sure that they're not limited when doing this. So what we do is we make it possible for our full text search queries, so the right-hand side of the @ operator, in this case, the keyboard here, to also accept the JSON. And we have a query builder on top of it so that you don't need to write the JSON yourself. You can write it in more like standard SQL syntax. And that gives users the ability to do things in a significantly more feature-rich way. So here's an example query of what this looks like in ParadeDB. Select star from the mock items, where we want to boost the query for shoes by 2 versus the description running. So really what we're looking for here is we're looking for running shoes, right? So this might be, Amazon, and excuse me, the user is looking for running shoes. But we're saying, hey, we want the value of shoes to be twice as important as the value of running. So probably if the user is looking for running shoes, they're more likely to be happy with search results that are other types of shoes than are like, I don't know, like running shirts, right? Or something like that. And so we want to make sure that we prioritize the word shoe. This gives the ability for the developer to go and build like the exact right search experience that they want. And at many of the big companies that make products that you use today, right, that are pretty primarily search-based, at Best Buy and Amazon and Reddit and Facebook and so on, they have entire teams that are dedicated to sort of constructing these complex queries in a way that is most likely to give the results that the user is looking for. So this is a very important part. In Elastic, their existing search database, this is called their query DSL. Lastly, and perhaps the most exciting part of our whole implementation, is something that we call the custom scan. So Postgres has this API, which is not very heavily used, that gives you the ability to the developer, in this case, our team, to control other parts of the query, not just what's on the right-hand side of our own operator. There's 3 things that this enables us to do. The first thing is it enables us to do predicate pushdown. So push down more of the query into our Tantivy fast search engine, which is optimized for this and so gives better performance. The second thing it enables us to do is the BM25 scoring. Right? So as I was mentioning before, this is very important, but in the previous 2-3 examples, we haven't really touched on how we do that. This is how we do it. And the third thing it enables us to do is fast aggregations or bucketing, right? Sort of, solving the problem that Postgres has of the slow counts and the slow group bys and so on. So let's take an example for all 3 of them. For predicate pushdown, let's say you have this query here. Select star from mock items where the description is keyboard and the rating is 5, is less than 5, excuse me. If we didn't have a custom scan, the way Postgres would work is it would do 2 different scans. It would first do a scan over the description, and it would do a scan over the rating field, right? And then it would combine the results. However, in our index, we said you want to put everything within the same index, so both of them already exist within the index. Wouldn't it be better if we did a single scan of the index and look for both rating and description? This is what the predicate pushdown part of the custom scan allows us to do. Excuse me. So again, you only have to do 1 scan instead of 2, and that significantly improves performance, especially at scale. The second component is the BM25 scoring. So when you have a query like this, where you say select star from mock item where the description is keyboard, how are we going to return the scores to the user, right? We need a way for the users to see those scores so they can decide how to return the results to their end users. Our custom scan allows us to project a new column into the result. So in the table that we work with, right, there's no score BM25. There's only the data that is relevant to the business data of the company or the application. However, we need to be able to return the score to the user. So what we do is as part of our custom scan, we project the score onto the result set. So when we run a query like this, we say, okay, we're searching for keyboard within the description field, we want the score ordered, the results ordered by the score, right? The most relevant results at the top, makes sense. And we add a clause here that we say ParadeDB score based on the IDs. And I will add an extra column to the result set to the developers that can then take actions in their applications based on those results. I used to have in this slide, an area where I showed it, but unfortunately it doesn't seem to be in this presentation. So I apologize. But you can, imagine it's simply another column to the right-hand side of the standard result set. Like, in this case, like the description will be there, the name and so on, the ID. And the BM25 score is just a floating point number, right? 2.1234, things like that. The last part that the custom scan enables us to do is the fast filtering or the fast bucketing, which is very important. Everyone that searches on Amazon or wherever, you might have done like, oh, you only want to see results that are less than $50, right? 4 stars and up. You only want to search songs within Taylor Swift's song repertoire. All of these are sorts of filterings and bucketing that requires these fast aggregation. So let's take an example query here. I want to select, count all the IDs and the description from the mock items where the description is keyboard. So in this case, I want to search from this table where the description is keyboard. But if I had millions and millions of these, that would be slow. And I'm returning the full set of results, right? So I'm searching, okay, show me the keyboards, but I want to see the total list of all results that are in the catalog. If there are millions, that's going to be very slow. So Tantivy has something in the library that we can take advantage of. It's called fast fields. What fast fields are is column-oriented storage. So in our custom BM25 index, we use these fast fields to store data in columns. Postgres stores data in rows. This makes it really, really fast for point lookups of searching for specific values. But if any of you are familiar with data analytics in general, you'll know that all the data analytics solutions out there store data in columns to make it faster to read the data on disk when you want to compute the total value of a specific column in your table. This is what we do here to have this sort of best of both worlds. So we can do this filtering really quickly in the index. So we return the count IDs in batches. In our case, a full Postgres page basically is the batch size that we go for, which is 8 kilobyte. And we can even parallelize this so that we have multiple Postgres workers that pull batches from our columnar index all in parallel, and then combine the results at the end. And that makes it significantly faster to do this count star. So if I want to search for, if you do a Google search, you'll see like the top 10 results on the front page, and Google will tell you at the bottom that there were 100 million results, right? This allows us to do this much faster. The result, in the sort of database nerd term, is we're essentially building a column-oriented vectorized processing engine. And this is a lot of jargon to say we're basically building an analytics database in a lot of ways inside Postgres, right? All the big analytical databases that you might think of, that's at the core, that's how they work. That's how they work. So why do people do this? There's a few reasons. First one, as I said, a lot of people don't really want to go to Elastic. They prefer to stick with Postgres. They know it, they trust it, right? We have a lot of customers that fit this bucket. Another reason people use it is for update-heavy workloads like e-commerce. There's a lot of e-commerce companies that we work with where their catalog is constantly changing, especially if you think of e-commerce companies that work with other vendors, right? Like delivery type companies or applications. The inventory is constantly changing. The price, the promotions, the availability in different stores can be changing. That's constantly updating the database, right? Tools like Postgres are really, really good at this, but Elastic not so much. So being able to do fast search on Postgres is very helpful for them. Another reason is for faceted search in SaaS applications. It's used in a lot of use cases. Just people build Jira and GitHub and so on, and everyone needs to search data. And then lastly, it's very common for people to use us for something called hybrid search, which is the combination of the vector search that I mentioned initially with this type of search. Nowadays, with AI being so prevalent, the vast majority of search experiences combine both, and you can get even more relevant results if you do both vector search and full text search. Full text search excels at searching specific keywords that don't really have a semantic meaning. Think like proper names, right? My name, the name of the president, whatever it may be, or like medical codes, stock tickers, like things like that, right? And then vector search excels at searching through things that have a semantic meaning, like a red t-shirt or a banana or whatever. Those words like carry some information about what they are. And so they're combined together very often. And then people deploy us in a variety of places on existing Postgres and so on. And that's it. That's what we do in the Postgres full text search world. And if you have any questions, I'm happy to answer them. Our work is open source. You can see it online, give us a star. And yeah, we hope it can benefit the community.
Thank you, Philippe. Do we have any questions? Anybody? That was a really good talk, Philippe. Thank you. It was very well laid out.
Of course, yeah, of course. Hopefully, I didn't cover it too quickly. Always happy, we're always happy to geek out on the work that we do. So if anyone has questions after, I'm available online, on social media and GitHub and wherever people find me. So feel free to ask.
Perfect. Thank you so much. I would also like to thank PGOS and PGX. Our next SFBay Pug will be Tuesday, February 11th with Language is a Virus, Managing Locales in PostgreSQL with Christophe Pettis. Upcoming conferences, FOSDEM is February 1st and 2nd at the University of Belgium. Scale 22X is March 6th through 9th in Pasadena, California. PG Day Chicago is April 25th in Chicago. We will send a link by email when the video is ready, and you can watch our social media. You can find us on LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We are looking for speakers for 2025, so if you or someone you know is interested, please contact us. Thank you so much. I hope everyone has a great afternoon, and we will see you next month. And thank you again, Philippe. That was a great talk.
Thanks for having me.
Sure. It was a pleasure. All right. Thanks, everyone.
Bye, everyone.
Bye-bye.